Professor Bhattacharya was the organizing chair of the Computational Linguistics Conference at IIT Bombay, December 2012. He also has been Associate Editor, ACM Transaction, Asian Language Information Processing. He has been PC member and area chair in ACL, OLING, IGC NLP, EMNLP, GWC, ICON and so on. Professor Bhattacharya has published extensively in top quality conferences and journals, about 200. He has guided 12 PhDs in AI and NLP and is currently guiding 10 PhD students. Professor Bhattacharya has been recipient of a number of prestigious awards and honors, speaker as expert in multilingual computation in the prestigious Dachstuhl Seminar, Germany, 2012, Yahoo Faculty Award 2011, Manthan Award 2009, given by Ministry of IT India and Digital India Foundation, IIT Bombay's P.K. Patwardhan Award for Technology Development 2008, IBM Faculty Award 2007, Microsoft Distinguished Research Grant in a Focused Area 2007 and United Nations Research Grant in 1996. Now I welcome Professor Bhattacharya to come in the stage and to deliver his lecture.
Good evening to all of you, and I would thank Mandar partner for giving me this chance to talk to you on a very contemporary and pertinent topic, which is machine learning. And since the focus of the workshop is machine learning, I thought I would sort of bring up machine learning methods in machine translation. So, as is well known, machine translation is a very well developed field and pretty ancient field, I would say, in computer science and engineering. This is a part of natural language processing, and natural language processing can be looked upon as an activity in 3 dimensions. Okay, namely the language dimension. There are different languages: Hindi, Marathi, English, French, and so on. And as we know from study of linguistics, each language has a personality of its own. Language properties are quite unique. Then there are problems involving text and language which need to be solved. So problems like morphological analysis, part of speech tagging, parsing, semantics, and so on. And they are all very important challenging problems of computational linguistics. The third dimension is the algorithm dimension, which is why computer science is interested in this kind of problems. Okay? Given a language and an NLP problem to be solved for this language, the task is to design an algorithm. It could be based on hidden markov model, CRF, MEMM, and so on, which are well-known machine learning algorithms to solve this problem. So it is useful to remember that natural language processing or computational linguistics is a 3-dimensional activity. Okay? And sometimes the temptation is to look upon natural language processing as applied machine learning. Okay, but that view is not really correct. Natural language processing has other aspects to it. Natural language processing also happens in layers. This kind of layering of tasks is pretty well established. So at the lowermost level is morphology, which is where words are processed. We break words into suffixes and also obtain their features. Okay. Going, for example, has the stem as go and indicates continuity of action. Pause tagging is part of speech tagging, namely words are categorized into nouns, verbs, adjectives, and so on. Chunks are groupings of words into meaningful segments. A very well-known example of chunk is adjective-noun combination. Okay, little blue bird, for example, is a chunk. In Indian languages, also one sees chunks in verbs. Okay, khata ja raha tha, for example. It's a verb group, and that's a verb chunk. Parsing is structuring of sentences into trees in the form of phrases, noun phrase, verb phrase, and so on. Semantics extraction is meaning extraction. Word association and the meaning that emerges from the sentence. Discourse and co-reference is the processing of text when multiple sentences contribute to meaning. So a paragraph, for example, or a chapter of a book and so on. So this kind of layering of natural language processing tasks is pretty well established. Now the point is that each layer, the ambiguity from the lower layer is resolved. Okay? That is the first important point to note, which is where machine learning plays its important role. Okay? So morphology. Sorry. Taking the phone side. Okay. So at the level of mouse tagging, when morphology returns multiple part of speech, okay, there is a disambiguation algorithm which plays on this output of morphological processing and produces a single output maybe as well as possible. So for example, the word bank can mean the action of dependence. I bank on you. Or it could mean a noun, and part of speech tagging isolates the possibility from the context. So at every stage, a layer performs disambiguation action on the output of the lower layer. Okay, that's a very important point to note. And this disambiguation is choosing from amongst possibilities, and therefore becomes a classification problem. Okay, this is where machine learning becomes relevant to natural language processing. Okay, so at each stage, one would perform a kind of classification, applying some machine learning algorithm, and this disambiguation is on the output of the lower layer. So, for example, part of speech tagging is typically done using hidden Markov model, which is a well-known graphical model from machine learning. And HMM would disambiguate the output of morphological stage from the context of the sentence. Okay? Similarly, parsing would disambiguate chunks, chunks would disambiguate part of speech, and so on and so forth. Now, NLP community is still looking for an architecture, with efficient architecture, which will have back and forth information processing, information transfer between layers to do this disambiguation. One cannot assume part of speech tagging, long distance dependencies during part of speech tagging. So some dependencies, some disambiguation will have to be done when semantics and parsing stages are reached. And at the stage, if information is transferred back to post tagging, then difficult part of speech can be deciphered based on this higher level information. Okay, so this is where, for example, deep learning has become relevant in natural language processing today. Okay. Multiple layer neural networks are used for doing this disambiguation process. Okay, so we go ahead. Now, machine translation is a branch of natural language processing, and these are some loose statements. Okay, the completeness is not in the sense of completeness of NP completeness theory. Okay, it is not as if we have an NLP complete problem which is converted to a machine translation problem in polynomial time and so on and so forth. This is not the intent. What is intended is that machine translation drives natural language processing. Natural language processing drives AI. AI drives CS. If you look at the history of computer science, artificial intelligence, and so on, many problems actually originated in the need to do text processing, language processing. And there is no doubt that machine translation is an extremely relevant problem in today's world. It's a multi-billion-dollar industry. All the major players like Google, IBM, Microsoft have great interest in machine translation. So, machine translation, as we know, translates from one language to another by automatic means. So, the approaches to machine translation can be divided into two broad categories. The first category is knowledge-based, rule-based machine translation. And a lot of computer science actually originated in this knowledge-based, rule-based machine translation. Since 1960s, there has been effort, especially during the Cold War days, to translate between English and Russian by automatic means. And that would happen by making use of rules. So under knowledge-based machine translation, we have two more approaches which are well established. One is interlingua-based machine translation. Japan was the country which was pursuing this approach quite intensely for a long time. So one hears of systems like Atlas, which is interlingua-based machine translation between English and Japanese. The other approach is transfer-based, and the most accurate and successful machine translation system today, namely SysTran, is based on transfer-based approach. So we will take brief looks at these approaches of machine translation to understand what exactly is involved in machine translation and why is machine learning required. The second broad approach to machine translation is data-driven, and this became possible because lots of parallel corpus became available for training a machine. We have translations of newspapers, we have translations of parliamentary proceedings, manuals, tourism reports, travelogues, and so on and so forth. And all these provide great amount of training data for a machine to be trained on automatic translation. So under data-driven approach, again, there are two big streams, which is example-based machine translation. Again, originated in Japan much before statistical machine translation. But there is no doubt that today's ruling paradigm is statistical machine translation, machine learning-driven machine translation. So the goal of today's lecture is to understand the basics of this approach and some current developments. Now we would like to understand why is machine translation a difficult proposition. What are the hidden difficulties? So I have chosen only one of the many problems, namely language divergence. This is a well-known problem and can be described in the following way. Languages have different ways of expressing meaning. And these ways of expressing meaning differ from culture to culture, language to language, country to country, and even from time to time. And within the same region, from dialect to dialect. Okay? So there is no doubt that that it's a reality. Languages express thoughts differently. And this divergence has again two categories. One is lexicosemantic divergence, the other is structural divergence. So back in 2002, we had done an extensive study of English in the language divergence in the context of machine translation. So to illustrate the notion of language divergence, I have taken this Finnish example, and I will not attempt to pronounce this string. This whole word, this whole string means, I wondered if I should sit down for a while. By the way, this will not be surprising to people coming from South India. Dravidian languages are extremely agglutinative. Okay? Lots of morphemes are put together, suffixes are put together to convey a large chunk of meaning. Many times that corresponds to a whole sentence. So if we look at the morphemes, east is to sit down, ahata is a verb derivation morpheme to do something for a while. So east and ahata together means to do something for a while. Isi is conditional suffix that corresponds to if. I wondered if. N is first person singular suffix I. O is question particle, and han is a particle for things like reminder. Okay. So there are lots of complex processing going on when we look at this word and see that the morphemes interact with each other to produce a complex meaning. Okay. So Finnish is one of the extreme examples where strong morphology imposes this kind of word structure. The other end of the spectrum is Chinese, where morphology is extremely loose. Okay, even positions can be varied. So sometimes we wonder as to how Chinese people understand the meaning of a sentence. A tremendous amount of contextual processing must be going on in the mind. Now some examples and categories of divergences. The first divergence we look at is conflational divergence. So the word vomir in French conflates to three words in English, which means to be sick. Okay? The English word stab conflates to three words in Hindi, chure se marna. Okay? Bengali is churi diye marna. So a word in English has to make explicit the instrument of action. Okay? The instrument is concealed in the English word. Okay? It is similarly, this Swedish word means in English escape plan. So let's remember this phenomenon. This phenomenon in today's parlance in statistical machine translation is called fertility factor. Okay? IBM model 3 is completely devoted to solving the problem of fertility. From linguistics, this term is known to be conflational divergence. The second divergence is categorical divergence, change in part of speech. The play is on. On is a preposition. If you translate this to any Indian language, most likely you will not get a postposition or preposition. You will have to introduce a complete verb. Khel chal raha hai. Khela cholche. Okay? So this on is a preposition, and its category has changed from preposition to a verb string. Chal raha hai. Okay. And when we look at these categories, let's also mentally think of algorithms, okay, which will close these divergences. Can we do it by rule, or can we learn it from data? That is the question. So a continuous question in our mind for machine learning is, do we have to give a rule, or do we have to learn it from the data? The next divergence is structural divergence. SPO to SOP. Peter plays basketball. Peter basketball khelta hai. The verb plays has moved to the end of the sentence. Okay? So subject verb object has become subject object verb. So this is a very common divergence. Japanese, for example, is SOV. So we believe the translation between Japanese and Hindi is an easier task compared to English to Hindi or English to Japanese. So now, what do you think? This divergence, solution to this divergence, will it emerge from the data, or can a simple rule be given? So if anybody has seen some NLP, he or she would say that this is a rule-driven problem. Just get the parse tree and invert the verb and the noun phrase. That's all. You don't have to go to data. So it is important to remember in machine learning when we should run to the data and when we should rely on human judgment and intuition. So this problem doesn't require machine learning. Head swapping divergence. Prime Minister of India, Bharat ke Pradhan Mantri, see that Prime Minister and India have swapped places. If you look up an off as a kind of river, then Prime Minister and India have exchanged places. Okay? So this is called head swapping divergence. This divergence also can be easily solved by making use of parsing and applying rules on the parsing. Constituent order divergence. Singh, the Prime Minister of India, will address the nation today. Bharat ke Pradhan Mantri Singh. So again, the order of constituents in this noun phrase, Singh, the Prime Minister of India, has changed when we have moved from English to Hindi. Adjunction divergence. She will visit here in the summer. In no Indian language can we keep this adjunct in the summer at the end of the sentence. Okay? वो गर्मी में वो यहाँ गर्मी में आएगी. So गर्मी में has to come in the middle of the sentence, or it can move to the front of the sentence. गर्मी में वो यहाँ आएगी. Preposition standing divergence is a very curious English language phenomenon. Who do you want to go with? So with and who are far apart. There is quite an amount of text between them. Indian languages do not allow this. Many languages don't allow this preposition stranding. The preposition is stranded from the noun. Okay? So maybe you would like to think on is this a machine learning problem or a rule-driven problem? So machine translation approaches have been categorized into different approaches, which I have shown before. Yeah.
As in case of Sanskrit, the sequence of words does not matter much. So is it easier to translate in Sanskrit relative to other languages?
So Sanskrit is said to be a free word order language. So your question is, from any language, is it easier to translate into Sanskrit? And that's because you are saying that one doesn't have to worry about the order of the phrases. Yes and no. Statistical machine translation will run into great difficulty for Sanskrit. Okay, so let's do some statistical FT and then you will see.
So, like semantic languages, can you just say the category languages?
Yeah. I should explain this again. Yeah.
Only the category.
Only the category. So if a good example of this is he was not very communicative. He was not very communicative in the model, let's say. So communicative is an adjective. In Indian languages, you cannot retain the adjectiveness of the word. वो सुबह बातचीत नहीं कर रहा. So now we go to an abstraction which is pretty old in machine translation called Bhattacharyya triangle. It is very old. It is from 60s. But point is that this particular structure keeps coming back to machine translation again and again. Any new development has to take cognizance of this structure called the Bhattacharyya triangle. So this triangle captures the fact that from the source sentence to come to the target sentence, I can come from the base of the triangle, or I can move slightly up on the left hand side of the triangle, then do a transfer to the right hand side, and then generate the target language sentence. The higher I go, the more analysis I have to perform on the source sentence. Okay? And from there, of course, I transit to the target language side and then generate the target language sentence. Now, the higher I go, the less is the distance between the two languages, the source and target language. At the tip of the triangle, we have deep understanding level, and then there is no difference between the source language and the target language. There is no divergence. Okay? All divergences have been absorbed into a kind of machine readable form, and the target language can be generated from this form. Okay? So this analysis, which is the process going up the left hand side of the triangle, involves various kinds of disambiguation. If you remember the natural language processing layers, moving up this left hand side of the triangle is equivalent to moving up the layers of natural language processing. Okay? How? So at the graphemic level, we obtain the tokens. At the morphosyntactic level, we obtain the part-of-speech tags. At syntagmatic level, we obtain part-of-speech tags and constituent parts. Then at higher level, we obtain dependency tree. At logico-semantic level, we obtain the semantic roles. Interlingual level, words and disambiguation has been done. And at the topmost level, speech acts also have been disambiguated. Okay? So this is complete natural language processing. Okay? So interlingual-based machine translation or deep meaning-based machine translation solves first a complete NLP problem and then solves a complete natural language generation problem. Okay? So this is what is involved in ideal machine translation. Now I really request you to reflect for 2 minutes on whether all this is necessary. Can machine translation be independent of natural language processing? A very strange question. But machine translation, lots of practitioners of machine translation do believe that natural language processing and machine translation can be leading from each other. Okay, why? Because you really don't have to go up this hierarchy so much. Now, can you give me an example where we could translate from one language to another at the graphemic level? Graphemic level, you remember, is simply isolating tokens. Okay? So, what kind of language will admit this? Almost zero analysis.
Computer language.
Maybe numbers. Language. Huh? Same script. No. Huh? Somebody said Hindi and Urdu. Dialects also no. Hindi and Urdu is almost graphic level translation. Often you just have to replace the Sanskrit word by Arabic word or Persian word and translation is done. आज मेरी परीक्षा है, आज मेरा इम्तिहान है. Okay, so languages which are this close, like Hindi and Urdu, almost the same language only with vocabulary difference, will admit graphemic level translation. Yeah.
So the script for Urdu is different. The way we read it, so how will that be taken care of?
Okay, so that's a script level issue. A script level issue. So that doesn't really come into the ambit of machine translation. I mean, it can be taken care of by post editing. But most languages require some amount of processing and then going to the target language side and producing the target language side. Okay. So, illustration of transfer, converting SQL languages to SOV. Okay. John eats bread. John roti khata hai. John roti khai, and so on. Most Indian languages will follow this order. And this can be very easily affected by applying a rule of transformation. VNP converted to NPV. Okay? This will very easily give me the sentence order correctly in the target language. But obtaining this tree amounts to going up the backward triangle up to some level, up to this level, and then applying the transfer rule, then generating the sentence. Okay? Now there is this universality hypothesis that at the level of deep meaning, that means at the tip of the triangle, all texts are the same, whatever be the language. All texts are the same, whatever be the language. Now, when we do analysis on the source language side, okay, many different problems have to be solved, and many of them are actually data-driven machine learning problems. So if I take this sentence, for example, Washington voted Washington to power. It's a very difficult sentence to process for a machine. So first Washington is the place Washington, the second Washington is US President Washington. So the problem that is getting resolved here is what is called the named entity recognition problem, which is routinely done using a data-driven approach. Okay? So Washington is a place, the agent of voting is Washington, and the object of voting is Washington again, the US President Washington, and the main verb is voting. Okay? Now this sentence is also metaphorical because what is implied is not Washington city, but people of Washington. So the kind of disambiguation which is needed for a complete and correct interlingual graph are name disambiguation, auto-speech disambiguation, attachment disambiguation, sense, co-reference, semantic roles. So here is an example. I went with my friend John to the bank to withdraw some money but was disappointed to find it closed. This bank, is it noun or verb? The first disambiguation. The second disambiguation is about John being the name of a person. John could be the name of a horse also. Okay. Then bank is financial bank or river bank. This is sense disambiguation. Then co-reference disambiguation. What was disappointed to find it closed? What does it refer to? Okay. And the final disambiguation is a difficult problem in NLP. Subject problem. I went with my friend John to the bank to withdraw some money, but was disappointed to find it closed. Who was disappointed? That needs to be resolved. So typical natural language processing tools which are used are part of speech tagger, Stanford, named entity recognizer, dependency parser, lexical resources like WordNet and so on. Okay. So a typical interlingua-based machine translation architecture will have this kind of NLP tools, and many times a complex sentence is divided into simple parts by a simplifier, and each simple part is treated separately and finally merged to produce the translation. Yeah.
Sir, I have a question here. Not on this exactly, on one of the previous slides.
Yeah.
For SOV to SVO kind of a conversion,
Yeah.
you said that this is where a rule-based approach is better because you can just get an inverted pass tree and get along. And for named entity recognition, on the other hand, you said a data-driven approach would be more appropriate.
Yeah.
So my question is that how do we understand that where, because even for named entity recognition there could be some rules which would help you identify named entities.
Yes.
But we would rather prefer a data-driven approach. So how do we understand that in which case what is better? Is a rule better or a data-driven approach?
Yeah. So let's wait till the talk is over.
Okay.
This is the question. This is the question. So now when we come to a generation of target sentences from the representation, the problems that we have to solve are lexical transfer, that means word mapping, morphological synthesis, how will the root word get transferred